All right, let's talk about something that every single ACI engineer runs into: endpoint connectivity problems. You know the feeling. One endpoint just can't talk to another, and it feels like you're looking for a needle in a haystack. Well, the good news is, with the right systematic approach, we can turn that haystack into a really clear roadmap. So let's dive in. Here's our game plan. First, we'll set the scene with the connectivity mystery. Then, we'll run through an initial checklist of the usual suspects. After that, we're going to get into the real meat of it, decoding both Layer 2 and Layer 3 forwarding. And finally, we'll pull it all together into one simple, powerful ACI troubleshooting framework. So let's picture this. You've got your fabric up and running, your apps are deployed, and things are looking good. Until, they're not. You get that ticket or that call from an application owner saying, hey, these two endpoints are supposed to be talking, but nothing. That's the core mystery we're here to solve today. In this diagram, this is our exact scenario. We've got endpoint 1 over here, let's call it EP1, and it desperately needs to communicate with endpoint 2, or EP2. They're both connected into our beautiful ACI fabric, but that traffic is just hitting a wall somewhere. That big question mark in the middle, we're about to make it disappear. This is it, isn't it? This is the million-dollar question. When you're staring at a problem like this, it can feel, a little overwhelming. Do you start firing up packet captures? Do you start rebooting things? The real key isn't just knowing what to check, it's knowing the order to check it in. Guessing just wastes time. Having a system gets you answers fast. Okay, before we start diving super deep into the fabric's guts, we need to check the basics. Think of this as the initial triage, the low-hanging fruit. A surprising number of connectivity issues come from just a handful of common problems we can check out pretty quickly. And these 4 culprits right here, they account for, I'd say, the huge majority of unicast forwarding problems. Maybe the endpoint just isn't even learned by the fabric. Or, hey, maybe it is learned, but a bad VLAN config or some other policy is blocking the way. And of course, simple typos and misconfigurations can cause faults that just stop everything cold. These are always our prime suspects. So here's our initial action plan. First things first, we check the endpoint's operational status, right there in the APIC GUI. Maybe use a handy tool like the endpoint tracker. Next, we'll peek into the COOP database. That's the Council of Oracle protocol, which is basically the fabric's address book, to see where it thinks the endpoint is. We have to confirm that from the leaf switches too, and we absolutely cannot forget about policies. We need to look for faults on the EPG, check our contracts, and make sure that whole chain of fabric access policies, AEP, domains, VLAN pools, all of it is solid. All right, so our initial checks are done. If the problem's still there, it's time to go deeper. We're going to start at Layer 2. Why? Because if you can't even switch frames inside a bridge domain, you're never going to get to routing. And to do this, we're going to use a really clear multi-tiered method. And this right here, this is the secret sauce. It's a simple but incredibly powerful escalation path. You always start with the GUI. Then you move to the CLI to get more detail, and only if you absolutely have to, you go down to the packet level. This tiered approach just makes sure we're being efficient and not bringing out the heavy machinery unless we really need it. We'll use this for both L2 and L3. So let's put this into practice. For Layer 2, our first checks happen entirely in the GUI. We're just validating, is the configuration what I think it is? Are there any sneaky faults hanging out on our EPGs or bridge domains? And most importantly, does the APIC actually show that our endpoints have been learned? Now, if the GUI looks clean but things are still broken, we drop down to the command line. This is where we find the ground truth. We're going to SSH into the source leaf and verify it's learned the source endpoint. Then we'll hop over to the destination leaf and do the same for the destination endpoint. And the crucial middle step, check the spine's COOP database to make sure it knows where both of them are. If there's a gap here, traffic's going nowhere. Okay, so what if the CLI checks out, but it's still not working? It's frustrating, I know. But now it's time for the heavy artillery, packet capture. We can use incredible tools like ELAM, the embedded logic analyzer, to see if the frame is even hitting the switch hardware. We can also use the ftriage app, which is awesome for tracking a flow across the entire fabric to see exactly where it's getting dropped. Okay, that was L2. But what if our endpoints are in different subnets and they need to be routed? Well, the great news is we use the exact same 3-tiered framework. The only thing that changes is the specific stuff we're looking for. Let's see how that works.
For our first layer 3 check, it's all about the basic programming. Is the pervasive gateway for the bridge domain actually pushed down to the leaf switches? Does the source leaf even have a route to the destination subnet? And you'd be amazed how often this is the culprit. Has the source endpoint actually resolved ARP for its default gateway? If any of these three are a no, routing is dead on arrival.
So once again, if the high-level GUI checks look okay, we escalate to the CLI. Now we're going to get our hands dirty and look directly at the forwarding tables on the switches themselves to see how the fabric has learned about our endpoints and the routes between them.
This right here is our essential toolkit for L3 on the CLI. We'll use show endpoint to see if the leaf has even learned the IP address. Then we check the tunnel interface to find the destination TP, the tunnel endpoint, for that remote leaf. From there, we make sure that TP is actually reachable in the overlay routing table. And finally, we're back to the spine, checking COOP to make sure the IP to location mapping is correct. And you guessed it, just like with Layer 2, our final deepest level of investigation is packet-level analysis. If all the routing tables and entries look perfect, but traffic just isn't getting through, Elam and Fit Triage become our best friends. They're going to tell us definitively if the packet is arriving and exactly what the hardware is deciding to do with it.
Whew! Okay, we have covered a ton of ground. We've gone from those high-level initial checks all the way down to the packet level for both L2 and L3. So now let's bring it all home and consolidate everything into one easy-to-use framework. And this table brings it all together beautifully. Seriously, think of this as your cheat sheet for ACI endpoint troubleshooting. It doesn't matter if it's an L2 or an L3 problem, you've got a clear, logical path to follow. Start in the GUI, get more detail from the CLI, and only when you have to, go to packet captures. Following this process will save you so much time and make you a way more effective troubleshooter. At the end of the day, the biggest thing I want you to take away from this is that troubleshooting a complex system like ACI isn't really about memorizing 1,000 commands. It's about having a repeatable, logical process. By moving methodically from the big picture in the GUI to the details in the CLI, and finally down to the packets themselves, you build a complete story of what's going wrong. This systematic approach isn't just a technique. It's the most powerful tool you have for mastering the fabric.